So, good afternoon. Thank you for the invitation. I would have loved to be here with you, but unfortunately, I have many other things to do here at the same time, and I had to choose, especially a conference very soon. You all have seen these videos, and you all know, if you're doing robotics, that robots fail a lot, very easily in many situations. We don't usually love to show this to people because, well, it's not very nice for the robot, so very uh, dangerous for the robot itself. And in our lab, we have been working on trying to address this issue, what to do when robots are broken. We mostly work with this small robot, which is much cheaper than the Atlas robot, so we can break it more easily and play with it more. And for instance, here we had a robot that was working. We unplug one wire, and the robot is not capable of working anymore. So the main challenge of my talk will be how can the robot adapt to damage and work again using some kind of learning and adaptation mechanism. So how can it just be able to continue its mission? Because I think that if we want to deploy robots for a long time, in real situations, they will somehow break or need to adapt their behavior to new situations. And we want to be able to do this for future robots. So there are many ideas, and in our lab, we work on most of them in the past. The first idea that you could have is we could use reinforcement learning directly on the robot. So we let the robot try things. We use some kind of direct policy search. So the robot tries to see what's working, what's not working. If the robot is moving forward, then we say, okay, it's the right path. The main challenge here is that if you want to learn with reinforcement learning on a real robot, and you want to use this for adaptation to a new situation, you need to be highly data efficient. So essentially, I would say that you expect the robot to learn in 1-2 minute stop, but usually something like 10 trials for locomotion. If it's more than this, then usually there's no point in adaptation. You cannot wait for 2 days for the robot to adapt to damage because it will run out of battery, it will be useless for the mission, and so on. So a good idea if you want to be more data efficient is to use model-based reinforcement learning. The general idea is you learn a model of the new dynamics using the data that you have. So this is not very different from trying to diagnose the problem. So you have a new model of your system, given the data that you have. Using this model, you can learn a new policy, or you could use something like model predictive control directly on the robot, on the model. And then you try what you have, your new behavior, you get new data, and then you improve your model of dynamics and so on. To make this faster, we use simulators of the intact robot as a prior, and it helped a lot. You can use Gaussian processes for model learning instead of neural networks because they tend to be much better when you have very little data. You could also use meta learning to try to have a model that can quickly be adapted to new situations. So all these ideas work, and I could have given a talk on all these ideas. But today I decided that I'd like to discuss about a different adaptation mechanism, which is a bit overlooked, I would say, in the current robotics and machine learning community. So what else can we do? Do we have another idea for adaptation that could be inspiring and could help us to approach this problem of adapting quickly to new situations? So what else? Dinosaurs. You probably all recognize this movie. Dinosaurs were on Earth, as you know, a lot of different species, big dinosaurs, small dinosaurs, tons of different animals and plants that are not alive anymore. But you also know how all of that ended. Of course, all the dinosaurs are not dead, but they're mostly disappeared because of a big catastrophic event on Earth that destroyed a very large part of life on Earth. But life survived. We still have life everywhere. So somehow life adapted. Life found a way to overcome this hugely catastrophic event and to strive now to still have a lot of different species, to have life everywhere from the deep sea to the sky and so on. And dinosaurs is just one event in the story of Earth. So we usually say that there were 5 main catastrophic extinctions, and numbers are really impressive if you look into them. So there are a lot of books and documentation about all this. So for instance, if you look at the Eurovision Silurian extinction, that's 85% of species that died, which, yeah, it's mind-blowing. Then Devonian is also 95%, and the dinosaurs, the Jurassic is, the Cretaceous Tertiary at the end of Jurassic, is 75% of species. So already 5 times in the history of Earth, we had these big extinctions with most of the species that disappear, and still we still have life after all of this. And the reason is diversity. Diversity is a powerful adaptation mechanism. So the reason why life survived to all these big extinction events is that it was very diverse. So for instance, let's say a meteorite arrives and a specific species, maybe it's living deep under sea, and then it's not affected there. So it can survive, and then by diversifying itself, then invade niches that were left by species that disappeared because of the big extinction event. Or maybe having a specific property, like, I don't know, being able to use less oxygen, maybe it's very helpful after this big extinction event. Or anything that's different might be useful for a future adaptation because you don't know what the future will be. So if you're doing things in a different way, then there is a chance of surviving. And the reason why life survived on Earth to all these extinction events is that it is really, really diverse. If you look at all the different species of plants and animals, you see they're all living differently, they're all doing things differently, and they're all ready somehow for some big change in a different way. So the question now is, could the robot adapt like species? So that's not like animals adapt, not like a specific animal during its lifetime, but much more like a species on a time scale much bigger. So can we do something that looks like this to help robots to adapt to a new situation? So we designed something like this, and the main algorithm is called map elites, which is an algorithm that's designed to find a diverse set of high-performing solutions to a problem. So a problem could be working as fast as possible. And you want to find many ways of solving this problem. So maybe you want to work, I don't know, using your legs in different ways, tilting your bodies in different ways. You want to find many species of working behaviors. If you just extend this a bit, you could say that you want to find many different ways of surviving. So maybe surviving in the deep sea, maybe surviving in the sky, maybe surviving on snow. All these are different behavioral niches. And for all of these niches, you have a species that dominates. So maybe the snow leopard is dominating life on snow in a country, for instance. And it's a very, very, very good animal for this specific niche. So the way we design this algorithm is that we have a feature space which defines what is to be different. So it's on the drawing here, we have 2 dimensions for this. We could have more. So you have 2 dimensions, and that defines a grid. And in each of these grid, we want the species that will dominate this specific combination of features. So that's what we call the elite. And to fill this grid automatically, to learn it, we use a variation of evolutionary algorithms. So we will randomly select one of the elites that we have. We had some variations, so some modifications, some random noise on the parameter, something like this. We simulate it, or we evaluate it in an environment. And from this, we deduce the features. So we look at how it behaves. Does it jump? Does it roll? Does it fly? Or something like this. And once we have identified the right niche, we look at what's already here. So if there's nothing, then the new species invades the niche. So it is the new dominating species. If it's not, then there is competition. That means that we look at the performance and we keep the best one. And then we do it again and again, and we let this run for a long time. So it looks like the classic genetic algorithms, but it's not, because the classic genetic algorithm is about optimizing the performance function, the fitness function. So at the end, you have a single best solution. Here, the result is many, many different species. So for instance, in typical examples, we have about 10,000. So at the end, we have 10,000 highly performing solutions that all behave differently because they all have features that are different, but they're all very good in their way if you look at things that are doing things in the same way. So here is for the six-leg robot. This is a different one behavior. And then we tried the features here are how much time each foot touches the ground. So we're not really preparing for damage here. We're just trying to say, let's find many ways of walking, but we want the robot to walk forward. If you just do random movements, then the robot does not move forward usually. It just turns around and turns out itself, or I don't know, do things that are not working. But if you say, I want many different ways of moving forward, for instance, this one is not using the first two legs. And if for some reason you need to avoid using these two legs, maybe they're broken or maybe there is something, I don't know, in the environment, then you're ready because you have a behavior that is not using the first legs. This one was especially fun. At the end, we had a robot that was not using any leg because it found a way to tumble over and then use the knee on the back. So then all these walking behaviors are organized in a big map. So this is a 6-dimensional map here. So every of these pixels is a different solution to the problem, which is moving forward here. And for all these pixels, we have the best one. So you see the color is not uniform because, of course, if you're only using 3 legs and mostly not using 3 other legs, you will not move as fast as using your 6 legs. But still, you have the best among all these ones. So maybe it's moving slowly forward, but it's still moving forward. So we have here 13,000 different ways of working, which is a very rich solution to the problem. So then we need to build meteorite because yes, we were ready for an adaptation. So we have all these 13,000 different solutions to the problem. And our hypothesis is one of them will work with a damaged robot. One of them is working, but we don't know which one. When you have a meteorite or something that like this big extinction event, then there is like a parallel evaluation. Everything is evaluated in parallel. What survives, and at the end, we only have the species that survived. But we have a single robot here. We don't have billions of robots that can try to survive. So we need a quick way of identifying among all these nice solutions which one is still working on the damaged robot. It's not too hard for 2 reasons. The first is that using this search for the elites, so for the high-performing species, what we did is essentially we had a big haystack with many needles inside, and we took all the needles out, and then we only have to search among the needles. So it's much easier to search among needles than in this big haystack. And then we organize everything in a 6-dimensional or low-dimensional space. So it's much easier to search in a 6D space than in a big space of, I don't know, in that case, it was more than 36, but we could have also neural networks with millions of parameters. So our idea is that we can search in that space among the solutions that we evolved, so among the solutions, the good species, using Bayesian optimization. So Bayesian optimization is a very famous algorithms. I'm sure many of you already know it. Just in a few words, the idea is we use Gaussian processes to model the objective. Gaussian processes is nice because they work very well for regression with a few points, and they give you an estimate of the uncertainty when you're far from points that you haven't tried, then you can explicitly know that you don't know, and then you can use this for exploration. Also, some nice thing is that we can use a mean function. So we can, instead of starting with I don't know anything, you can use a mean function that already has a shape. And in our case, we can use the mean function that comes from our simulations. So the concept of Bayesian optimization, we learn the Gaussian process from using a few random points. So we pick up like 3-4 points. Then we model the objective function, which is how far we have been walking, how fast we're walking with this robot. So we have a model of the function. When we use this model to select the next point, and for this there are many ways of doing it. The simplest way to understand is the upper confidence bound, which is essentially what we maximize is the predicted value plus the variance predicted by the model. So that will help us to explore. So we say we want something which is good, predicted to be good, and in a part that is not well explored. When we take this point, we evaluate it on the way robot, we update the model because of a new point, and we loop over this until we're satisfied with the solution. So this is the full algorithm. Offline, there is an evolution-based search for the best species. So this is using the intact model of the robot. It's using a simulation. It's not a perfect simulation at all. And it's creating diversity. It's creating many ways of solving a problem. So we do this before deploying the robot. And online, if something happens on the robot, then we search among all these solutions in this diversity of solution for the solution that still works on the robot using Bayesian optimization. So this is what we got. Here we had 36 parameters to learn, but we could have used a neural network because all the search for species actually is in simulation, so we could spend as much time as you want. And you will see here all the trials on the real robot. So the first ones did not work that well, but you could also observe the diversity of things. So observe that the robot is trying very different things, very different ways of solving the problem. It's not just optimizing locally and trying to tune parameters. It's really trying to do something very different. And here, after something like 30 seconds of learning, we got a good solution. This one did not work very well, and at the end we stopped. So after 40 seconds, we get this nice and dynamic gate, which was fully learned on the real robot using ideas that came from the simulation, and that works on the damaged robot in spite of this leg that is here moving. And that's also very hard to model. If you were trying to model this damage, that would be difficult because the leg is moving. And you have no sensor to sense the motion of the leg here, so the broken leg. And the robot is jumping actually, so not the kind of things I would have designed myself to recover from this damage, but it's moving forward at a very nice speed and solving the problem. So we did this on many other damage conditions. It worked. For instance, here we cut the leg in two, and after 25 seconds of learning, the robot worked again. We also did it on other robots. So, for instance, on this 4-leg robot, here we blocked one of the legs, and after 6 episodes, yeah, it was a bit longer, like 10 seconds per episode. It found a way to limp and to adapt to this specific damage. So, for instance, if you start, you usually get this kind of behaviors that are not very helpful on this damage robot, of course. And you can extend this using other ideas. Here we didn't anticipate for damage because we really wanted to see adaptation. Like I have no idea about what could happen to my robot, but in the practical use, it will make sense to say, okay, I cannot anticipate that maybe I will lose a leg. And then you can essentially learn one map for every situation with a missing leg. So here you would have like six maps instead of one, and that means instead of having 13,000 solutions, you have 6 times 30,000, so something like 80,000 different solutions, and then you search among them with Bayes optimization which one works on the damaged robot, and you can find solutions using this prior as well as as all the diversity that you found. It's like having more diversity essentially. And we designed an algorithm for this a few years ago, just to show what kind of things. Here, the robot is doing different gates because we increased the search space, so it was capable of using also the last join by itself. And so that's why it's moving a bit differently, but essentially we can learn also in 5 episodes to adapt to this damage. So before concluding, I wanted to say that this is cheating still for adaptation because this is episodic learning. So in that case, the robot was magically put back in its starting position, so every trial was comparable. The idea would be ultimately to learn without reset. So we want to take the environment into account, obstacles, and so on. And so we want the robot to be able to, we say, let's go to this waypoint, let's go to this point, and the robot is broken, and you can still achieve the mission. So in that case, we know a dynamic simulator of the intact robot like before. We know the environment, so we assume that there is some SLAM algorithm, something like this, but we don't know the damage, and we want to learn why doing. So why there was, we can still use this map edit algorithm, but instead of searching for many ways of working, we search for gates that go in every direction. So we try to fill this grid here with the end position of the robot after 5 seconds here. So we will have things that go forward, backward, slowly, fast, right, left, and so on. So we still have a lot of diversity, but in different space. So we get all this here. So every of these points here is a different behavior that leads to this point, and you see the end direction is a small arrow. So it's a nice repertoire of things. And the idea is that we will adapt this repertoire by bending it. Like if you want to go forward, and actually because the robot is broken or because there is a weighty gap, you went slightly right, then you say, okay, I will change the predicted outcome of this repertoire of different gates to be slightly right. And then that will bend the neighbors and so on, and you will bend this picture using real data. So then we need an algorithm to decide what to do next. For this, we can use a planning algorithm. So we will chain 3 seconds behaviors, and we can use a Monte Carlo tree search because it can somehow use the uncertainty about the predictions. So you can, for instance, not go too close to an obstacle if you're unsure about the outcome of a specific gate. So this is what we got with this algorithm. So at the beginning, the robot does not work at all because, well, it has a broken leg and it doesn't expect this behavior to do this. But after each of these 3 seconds things, it updates the repertoire, so the expected outcome of each of these elementary gates. It updates the neighbors too, because we use the Gaussian process to bend this space. And then it replans and do it again. So here at the beginning, it's trying to move forward, didn't go that well, but now it found a way. So it starts to walk forward and tries to reach the point. So the gate is not as impressive as before, I would say, but it's much more useful because here we have an operator that could say, I want to reach this point, and you can actually reach it in spite of the robot, thanks to the diversity of gates that you have prepared before. And here we are not touching the robot at all. So you see there is a cable. There's a, big reality gap here compared to the simulations. The robot is behaving very differently. We have a damage, we have a cable, but still we can control it to go to the point. And you see that for the second target, it was mostly moving. Here it decided to, I don't know, turn on itself for some reason. But essentially, we can finish the mission in spite of this damage, thanks to this diversity. So we have reached the second point, and we can continue like this. So it's much better than simple replanning because we learn from our mistakes here. Of course, it does not work for everything. For instance, this is one of the robots we have in the lab. Here we break one of the knees. And you cannot adapt to this kind of damage because the robot falls and you cannot try again. So on the hexapod, on the 6-leg robot, we can do we can adapt by trying or try to find something. But here, for this kind of robots, you really need something which is more like a reflex, something that is pre-wired. You cannot adapt to the new damage directly like we did for the 6-leg robot. So we have different set of solutions for this kind of reflexes that are also learned, mostly in simulation too. Okay, so to conclude, I think diversity is preparing for the unknown, and that's something we have been using for billions of years. And I think it's one of the main adaptation mechanism of life is by finding many solutions, then you have a chance if something new happens to be already ready. So I think it's a powerful adaptation mechanism, which is very much overlooked in machine learning research. And I think we should spend more energy in trying to get diversity. So the way I've introduced diversity here is for behaviors, but I think in many, many situations, if we were capable of generating not one optimal solution, but many different ones, then it will be much easier to adapt by using this diversity as a repertoire, as a or as some source of possible solutions that we can use to adapt quickly. So one way to get diversity, the one we used here, is something that we call quality diversity algorithms. So I introduced quickly the map elites algorithm, which is the algorithm that we introduced in 2015 for this. But since then, a lot of algorithms have been published for this. It's a very much growing field in evolutionary optimization. So could be for searching for behaviors for robots, could be for any optimization or even learning problem, when you need to find many solutions that are also good in their own way. They are all different, but all high performing. And so there are many papers. So if you want to start working on this kind of algorithms, if you're curious, here are 3 papers that could be a good start for this. But of course, you can just use your favorite search engine to search for quality diversity, and you will find many algorithms and work about this kind of techniques. Thank you for your attention. If you have questions, I of course have time for all of this.